Welcome to Animal Uncovered, the podcast where we explore the most unbelievable life cycles in the natural world. From the moment life begins to the moment it ends, nothing is as simple as it seems. Somewhere in the flooded grasslands of Venezuela's Llanos, as the wet season reaches its peak, the world above the waterline has gone quiet. Not the quiet of absence, but the quiet of something held in suspension, of breath not yet taken, of an event that is about to change the shape of things. Beneath the surface of a wide tea-brown river, a shape drifts in the current. It is massive, longer than a family car, heavier than a grown man and a half. Its olive-green body is dappled with black rosette markings, each one a near-perfect circle, like stones dropped into still water and frozen at the moment of impact. The pattern is beautiful in the way that many dangerous things are beautiful, quietly, unassumingly, with no announcement of what it means. The animal is a female green anaconda, and she is not eaten in 7 months. She is not starving. That is the remarkable thing. She's been gestating, carrying within her body a clutch of developing young, fed by her own reserves, sustained by fat stores that she has been burning slowly, steadily, like a candle set to last a season. Her metabolism has restructured itself around this purpose. Her heart rate has slowed. Her digestion has quieted to almost nothing. She has become, in a very real sense, a life support system. A vessel organized entirely around continuation. Now, in the murky warmth of a shallow backwater, she has sought the shallows. She lies half submerged beneath a curtain of floating vegetation, and something is beginning. A muscular ripple passes along the length of her body. Then another, 20, perhaps 30 minutes pass. Then, with little ceremony, because nature rarely offers ceremony, a small glistening form slides free of her body and into the water. Then another. Over the next several hours, between 20 and 40 individual snakes will be born into this river. Each one is roughly 60 centimeters long, about the length of a human forearm, and each one is fully formed, fully patterned, and fully on its own. Their mother will not look at them. She will not curl around them or guide them toward the shallows. She is already given everything she has to give. Her body is depleted, her mass reduced by as much as a third. She will slide away from the birthing site alone and begin the long work of rebuilding. The newborns scatter. Some head immediately for the surface grasses. Others disappear into the murk below. They carry no instruction manual, no memory of their mother's movements, no warning about what waits for them in the flooded forest and the open river beyond. And yet something extraordinary is already happening. Something that, if you trace it all the way forward through time, through years of hunting, growing, shedding, surviving and reproducing, will produce one of the most formidable animals on Earth. This is the life cycle of the green anaconda, and it begins, as all lives do, with nothing more than survival. Part 1. Why this animal matters. The green anaconda, Eunectes marinus, occupies a peculiar place in the human imagination. It is simultaneously one of the best known and most misunderstood animals on the planet. Ask most people what they know about anacondas, and they will tell you they are enormous, the biggest snakes in the world, and that they eat people. Both of those claims require significant qualification. The second is almost entirely false. The first is only partially true, and in the most interesting ways. The green anaconda is not the longest snake species on record. That distinction belongs to the reticulated python of Southeast Asia, which can exceed 8 meters in exceptional individuals. But the anaconda has the reticulated python beaten in every other meaningful dimension. It is the heaviest snake alive, the most massive serpent currently on Earth. Adult females, who grow considerably larger than males, have been reliably documented at lengths exceeding 5 meters and weights surpassing 90 kilograms. Exceptional specimens push beyond those figures. In a world where most snakes weigh a few hundred grams, the green anaconda exists on a scale that feels almost wrong, like a creature from a different evolutionary chapter that somehow persisted into the present. This mass creates a paradox. The anaconda is built for the water. It spends the majority of its life submerged, or at least semi-aquatic, using the buoyancy of water to support a body that would be cumbersome and slow on land. In the water, it is almost graceful, gliding through flooded vegetation, hanging motionless in the current, surfacing with such minimal disturbance that a person standing 3 feet away might not notice it until the water around their ankles shifts. On land, it moves with deliberate, rolling, muscular waves, not fast, not elegant, but entirely purposeful. It lives across a vast swathe of South America, the Amazon and Orinoco river basins, the Pantanal of Brazil, the Llanos of Venezuela and Colombia, the Guianas. Wherever there is slow-moving or still water, abundant prey and warmth, there's a reasonable chance that somewhere beneath the surface an anaconda is watching, and that watching, that patient, almost geological stillness, is at the heart of what makes this animal so fascinating. We tend to project urgency onto predators. We imagine them in constant motion, always hunting, always alert. The green anaconda inverts that assumption entirely. It is a predator built on patience, on metabolic efficiency, on the capacity to wait longer, stay stiller, and strike with more precision than almost anything else in its environment. It can go weeks, sometimes months between meals. A single large prey item can sustain it for half a year. In a world of scarcity and competition, this is not laziness. It is a survival strategy of extraordinary sophistication. The question at the centre of this episode is not simply how big the anaconda gets, or how it kills. Those are the questions that sell tabloid headlines. The real question is, how does a single newborn snake, 60 centimetres long, weighing less than 100 grams, abandoned in a flooded river, become something that can overpower a caiman? What is the shape of that journey? What does it demand? What does it cost? That is what we are here to understand. Part 2. Evolution and Origins. To understand where the green anaconda comes from, we have to travel back, not just decades, but tens of millions of years, to a time when snakes were only beginning to establish their dominance over the reptilian world. Snakes themselves are ancient. Their earliest ancestors diverged from lizard-like reptiles somewhere in the mid-Cretaceous period, roughly 100 million years ago. The exact origin of snakes, whether they evolved from burrowing ancestors or aquatic ones, has been debated for decades. What is clear is that by the time the dinosaurs disappeared 66 million years ago, snakes were already diversifying rapidly, filling ecological niches that the extinction had emptied. The family to which the anaconda belongs, Boidae, the boas, represents one of the older branches of the snake family tree. Boas and their relatives are considered by many herpetologists to be among the more primitive of the large snake groups, retaining certain anatomical features, vestigial remnants of a pelvic girdle, for example, visible as small claw-like spurs near the base of the tail, that their more derived relatives have lost entirely. These are physical echoes of the snake's limbed ancestry, small, almost apologetic protrusions that serve, in modern anacondas, primarily a role in the mating behaviour. The genus Eunectes, the anacondas specifically, is thought to have originated in South America, likely diverging from a common ancestor with Old World pythons tens of millions of years ago, after the continents had separated. South America spent much of its early history as an island continent, isolated from North America and from Africa, and this isolation drove extraordinary evolutionary diversification. The anaconda's lineage evolved in response to a specific environment: warm, shallow, slow-moving water, dense tropical floodplains, a world where ambush was more valuable than pursuit, where aquatic stealth was the key to survival. There are actually 4 recognized species of anaconda today. The green anaconda is by far the largest and most studied. The yellow anaconda, the dark-spotted anaconda, and the benny anaconda are its smaller relatives, distributed across different parts of South America. A 5th species, the northern green anaconda, was only formally separated from the green anaconda in 2024, when genetic analysis confirmed that populations in the Orinoco Basin and Trinidad represented distinct evolutionary lineage. This is a reminder that even for the most iconic animals on Earth, our understanding is still developing, still being refined by the tools of modern science. The giant constrictors of the world, anacondas, pythons, boa constrictors, represent what biologists call convergent evolution. They have arrived at similar body plans through different evolutionary paths in different parts of the world in response to similar ecological pressures. All of them share the strategy of constriction, not crushing prey to death, as is commonly believed, but suffocating them, tightening with each exhale until the heart can no longer beat and the blood can no longer circulate. This method of killing is estimated to have evolved independently at least twice in snake history. It is, in evolutionary terms, a winning strategy, and the green anaconda has refined it to its ultimate expression. Part 3, the life cycle. Phase 1, birth and the first hours. We return to those newborns in the shallows. Unlike the eggs of pythons, which are laid, incubated externally and tended by the mother's coiling body, anaconda young are born live. The green anaconda is what biologists call viviparous. Her eggs are retained inside her body, where the embryos develop within thin membraned sacs, nourished not by a placenta in the mammalian sense, but by yolk reserves and to some degree maternal secretions. The pregnancy lasts between 6 and 7 months. During this time, the female becomes increasingly sedentary, basking more frequently to maintain the elevated body temperatures that accelerate embryonic development. She eats rarely, if at all. When birth arrives, each neonate emerges enclosed in a transparent membrane that it ruptures almost immediately upon contact with water. Within seconds of entering the world, a newborn anaconda is swimming. Within minutes, it is hunting. This is not metaphor. These animals arrive fully equipped. Their scales are already patterned, the distinctive olive-green ground colour interrupted by black oval markings and a row of yellow-centred spots along each flank. Their teeth are already in place, rows of recurved, needle-sharp structures designed not for chewing but for gripping, for holding prey against the inevitable forward pull of the swallow. Their heat-sensitive pit organs, positioned along the upper and lower lips, are already functional, capable of detecting the infrared radiation emitted by warm-bodied prey animals, essentially allowing the snake to see heat differentials in complete darkness. They are born, in other words, as predators, small ones, vulnerable ones, but predators nonetheless. The first weeks are the most dangerous of an anaconda's life. A 60-centimetre juvenile is itself prey to a remarkable diversity of animals: herons, storks, large fish, caimans, and even adult anacondas, which are not above cannibalism when the opportunity presents itself. Mortality during this period is high, though precise figures are difficult to gather from field studies. Estimates suggest that fewer than half of newborn anacondas survive their first year. Survival in these early weeks depends on concealment. Juveniles quickly disperse from the birth site and seek the densest possible cover. Floating mats of aquatic vegetation, tangled root systems at the water's edge, the thick debris accumulation of flood margins. Here, their patterning provides extraordinary camouflage. The dappled olive and black design breaks up the snake's outline against backgrounds of leaf litter, shadow, and dappled light in ways that can make a 30-centimetre snake effectively invisible at a distance of 2 meters. They begin feeding almost immediately on small fish, frogs, tadpoles, and invertebrates. Every meal matters. Every gram of protein is an investment in growth, and growth, for the juvenile anaconda, is the most urgent business in the world. Phase 2. The juvenile phase. The green anaconda is a relatively fast-growing snake during its early years, though growth rates vary considerably based on prey availability, temperature, and individual genetics. In the first year, a well-fed juvenile may double or triple its birth length. By the end of its second year, a young anaconda might reach 1.5 to 2 meters in length, still vulnerable to large predators, but beginning to outgrow its earlier vulnerabilities. Growth in snakes is tied to feeding with a directness that mammals simply do not experience. A mammal maintains its size whether it eats well or poorly. It simply burns through reserves. A snake, by contrast, can shrink. Prolonged fasting in juvenile anacondas does not just consume fat reserves, it begins to metabolize muscle tissue as well. The snake literally becomes smaller. This is not unique to anacondas, but it has particular significance for a species whose survival strategy depends so heavily on achieving large body size. Shedding, or ecdysis, occurs frequently in rapidly growing juveniles. As the snake grows, its outer layer of scales, which is technically an extension of the epidermis rather than a separate structure, becomes too tight to accommodate the expanding body beneath. In the days before a shed, the snake's eyes take on a milky blue-grey opacity as fluid accumulates between the old skin and the new layer forming beneath it. The snake becomes temporarily less visual and more vulnerable during this period. It tends to become reclusive, hiding in damp, confined spaces that help loosen the old skin. When the shed finally occurs, the snake pushes through vegetation or debris, peeling back the old skin from the snout backward in one continuous piece, like a glove being pulled inside out. What emerges is startlingly vivid. The new scales are bright, richly coloured, their surface waxy smooth and almost luminescent in certain lights. The juvenile anaconda sheds several times a year during periods of rapid growth. Adults who grow more slowly may shed 3 or 4 times annually. Each shed is both a physical renewal and a marker of time, a record of growth that the snake itself carries no memory of, but that tells researchers a great deal about an individual's history and health. During the juvenile phase, the anaconda is also developing its hunting repertoire. Early prey items are largely aquatic, small fish pursued in shallow water, frogs ambushed at the water's edge. The juvenile is learning in a purely sensory and instinctive way to read its environment. to interpret the electrical vibrations in the water produced by prey movement, to triangulate the heat signature of a warm-bodied animal against the cooler background of water and mud, to hold itself absolutely still as a target approaches, and to calibrate the explosive muscular contraction that transforms stillness into strike. This is not learning in the way we might apply that word to a primate. There is no deliberate practice, no trial and error reasoning in any conscious sense. But the neural pathways are being etched by experience nonetheless. A juvenile anaconda that has caught a dozen fish is more efficient at catching the 13th than it was at catching the first. Phase 3. Sexual maturity. Green anacondas reach sexual maturity at different ages depending on their sex, and here is where the species' extraordinary sexual size dimorphism becomes relevant. Males mature earlier, typically around 2 to 3 years of age, at lengths of roughly 1.5 to 2 meters. Females take considerably longer, 4 to 5 years, sometimes more, and they must reach a significantly greater body size before their reproductive systems become active. A female anaconda first capable of reproducing might be 2.5 to 3 meters long and weigh 20 to 30 kilograms. This difference in maturation is not incidental, it is driven by reproductive biology. A female anaconda's reproductive investment is enormous. She will carry developing young inside her body for months, burning through fat reserves at a rate that requires a substantial energy baseline to begin with. Reproducing before she's accumulated adequate body mass would be physiologically counterproductive, potentially fatal. Her body, quite literally, will not allow it before the time is right. Males, by contrast, invest in reproduction primarily through the effort of finding and competing for females. They are smaller, rarely exceeding 3 meters in the wild, typically closer to 2, and their energetic investment in any given reproductive event is far less than the females. This disparity in reproductive cost is reflected in every dimension of the male's biology. He's built for mobility and detection. She's built for size and endurance. Phase 4. Mating. The green anaconda's mating system is one of the most dramatic in the animal kingdom, and it centres on a phenomenon known, with no small amount of justification, as the breeding ball. In the months at the end of the dry season, as water levels begin to rise and the flooded season approaches, something changes in the behaviour of anacondas across the floodplain. Females begin to move differently, more actively, more purposefully, leaving scent trails in the water and along the mud margins of the river. These chemical signals, deposited via specialized skin glands, function as advertisements. They carry information about the female's reproductive state, her size, her condition. They drift through the water column and along the ground, detectable to any male whose chemosensory system, those flickering forked tongues that continuously sample the air and water, picks up the trail. Males respond to these signals by following them with remarkable persistence, and they are not alone. Multiple males, sometimes as many as a dozen, may converge on a single receptive female simultaneously. The result is the breeding ball, a writhing compressed mass of snake bodies in which a single large female is entirely encircled by competing males, each one attempting to align with her body, locate her cloaca, and achieve intromission with one of his 2 hemipenes. The breeding ball may persist for days, weeks, in some documented cases. The female has considerable influence over the outcome. She can tighten her muscles, shift position, dislodge males she does not favour. Larger males often displace smaller ones through sheer physical leverage, pushing competitors away through sustained muscular pressure. The male's small pelvic spurs those vestigial remnants of ancestral limbs we mentioned earlier, play an active role here. He uses them to stimulate the female, scratching gently along her sides in patterns that appear to signal his identity and condition. This is, for the males, an extraordinarily costly endeavour. They eat nothing during the breeding period. They expend enormous energy in sustained muscular competition. Some males emerge from breeding balls visibly emaciated. Some may die. The female too pays a cost. Her breathing can be restricted when she is heavily surrounded, and the sustained muscular compression from multiple males creates real physical stress. But the outcome is continuation. One or more males will fertilize the female, and the long gestation will begin. Phase 5. Gestation and the long fast. The 6 to 7 months that follow fertilization represent an almost meditative phase in the female anaconda's existence. She is no longer actively hunting in any meaningful way. She is withdrawn to warm, shallow water, where she spends hours basking at the surface, absorbing the thermal energy that accelerates embryonic development. Her movements are slow and deliberate, the mass in her abdomen shifting her center of gravity in ways that make terrestrial movement especially laborious. She's burning herself to build others. Studies on large female constrictors during gestation have documented dramatic decreases in body condition. Animals that enter pregnancy at peak condition, emerging from it gaunt, their ribs visible, their once firm musculature softened by catabolism. The female may lose 20 to 30% of her pre-pregnancy body mass over the course of gestation. This is not a failure of the system. It is the system working as designed. She's a biological furnace, converting stored energy directly into the next generation. The litter size varies with the female's body size, a direct relationship that makes each additional meter of growth a meaningful reproductive investment. Small females at their first breeding may produce 15 to 20 live young. Exceptionally large females, individuals exceeding 5 meters, have been documented producing more than 80 offspring in a single litter. The average falls somewhere in the range of 20 to 40. Phase 6. Birth and the cycle begins again. And so we return to where we began, the flooded backwater, the mother depleted and motionless, the newborn scattering into the water with the instinctive urgency of the newly arrived. The cycle has turned. But it is worth pausing here to note something that is easily overlooked in the spectacle of birth. This moment is also the beginning of the female's recovery. Once her young are born, the female is free to hunt, to feed, to restore the reserves that reproduction has depleted. She will eat voraciously in the weeks and months following birth. Large meals, taken more frequently than at any other point in her year. Capybaras, spectacled caimans, large fish, whatever the floodplain offers. She is rebuilding herself, preparing whether she knows it or not for the next cycle. Female anacondas do not breed every year. The energetic cost is simply too great. Most females reproduce once every 2 to 3 years, with the interval depending heavily on how quickly they can restore their body condition after the preceding litter. This reproductive conservatism is part of what makes the anaconda's population dynamics so different from those of smaller, faster reproducing snakes. It is a slow life, measured in large increments. Phase 7, Old Age and Death. The maximum lifespan of wild green anacondas is difficult to determine because long-term tracking studies on large free-ranging individuals are exceptionally challenging. Captive anacondas have lived to 30 years. Wild individuals almost certainly live somewhat shorter lives on average, given the demands of their environment. A large female in the wild might reasonably be 15 to 20 years old. The very largest individuals, animals of truly exceptional size, may be older still. There is no sharp demarcation between mature adult and old adult in anaconda biology. Growth continues throughout life, slowing but never entirely stopping. A 30-year-old anaconda is not distinctly different in biology from a 20-year-old one, except that it is larger and has accumulated more reproductive history. The body does not senescence in the dramatic way that mammalian bodies do. There is no menopause, no obvious physical decline, no sudden cellular collapse. Death, when it comes, is more likely to arrive from the outside than from within. Predation, though rare for a large adult, does occur. Drought, which can strand anacondas in shrinking water bodies exposed to high temperatures and reduced prey, kills individuals that cannot reach adequate water in time. Injuries from prey animals, from competitors, from the simple mechanical stress of a physically demanding life, accumulate over years, and yet, for those that survive, there is a kind of permanence about the anaconda. A large female lying in the flooded llanos at the age of 20 has outlasted the individual lifetimes of hundreds of the prey animals she has consumed. She has presided over decades of wet seasons and dry seasons, floods and droughts, the rising and falling of the river. She is, in a very real sense, a fixture of her landscape, an anchor point in the ecosystem around which other lives have been organized. Part 4. Biology and Adaptations. To understand how the green anaconda achieves everything we have described, we need to look at the machine itself, the extraordinary biological architecture that makes this animal possible. Begin with the body. An anaconda's skeleton consists of the skull and an extraordinary number of vertebrae, anywhere from 300 to 400 individual bones, each one connected to a pair of ribs, and articulated in ways that allow the almost liquid lateral movement we associate with snakes. There is no sternum, no breastbone to limit the expansion of the rib cage. This is crucial for swallowing, because an anaconda's prey items are not small. They are often wider than the snake's own head. The rib cage can splay outward during swallowing to accommodate a bolus of food larger than the snake's resting diameter. The skull itself is a marvel of flexible engineering. Unlike the rigid skulls of most vertebrates, the anaconda's skull is built around a series of kinetic joints, connections between bones that allow independent movement. The two halves of the lower jaw are not fused at the front but connected by an elastic ligament, allowing them to spread apart independently. The quadrate bone, connecting the lower jaw to the skull, can rotate to effectively deepen the gape, creating the remarkable capacity for expansion that enables an anaconda to swallow prey many times the size of its resting head diameter. Each side of the jaw moves independently during swallowing, in a kind of alternating ratcheting motion, walking the prey backward into the throat. The teeth are recurved and numerous, rows of small, backward pointing hooks that grip without cutting, ensuring that prey moves in only one direction, inward. Anacondas have no venom. They do not need it. Their killing method is constriction, and it is mercilessly efficient. When an anaconda strikes a prey animal, it does so with explosive speed, the body uncoiling in a fraction of a second, the head driving forward with the force of muscles that have been under tension, coiled and compressed like a spring. The jaws seize the prey, and almost simultaneously the body begins to wrap. The first loop forms around the prey's chest, then another, then another. Each loop is positioned so that the snake can tighten them independently. and each time the prey exhales, the snake tightens. Not to crush the rib cage, though that can happen, but primarily to prevent the chest from expanding again. Without expansion, the lungs cannot fill. Without lung function, oxygen delivery to the blood ceases. The prey loses consciousness within seconds, and within minutes the heart has stopped. This process is measurable. Research has shown that constricting snakes can exert pressures exceeding 300 millimeters of mercury on their prey, a force that impairs cardiac function directly, in addition to the respiratory effects. The anaconda's constriction is not a blunt instrument, it is a targeted physiological intervention. Digestion in anacondas is equally remarkable. After swallowing a large prey item, which can take anywhere from 20 minutes for a small animal to several hours for something the size of a deer or a small caiman, the anaconda's digestive system undergoes a rapid and dramatic upregulation. The gut, which has been in a state of near dormancy between meals, rapidly increases in size and metabolic activity. Stomach acid production surges, intestinal tissue thickens, the liver and pancreas dramatically increase their output. Within 24 hours of a meal, an anaconda's digestive organs may double in mass. This is metabolically expensive. The specific dynamic action of digestion in a large meal can account for a significant proportion of the animal's total energy expenditure. But it allows the anaconda to maintain its organs in a low-cost dormant state between meals and then rapidly bring them online when needed. This is metabolic flexibility of a kind that mammals simply cannot match. The anaconda's sensory systems are built for an aquatic and crepuscular world. The eyes are positioned on the upper and lateral surfaces of the head, providing a view primarily upward and to the sides, perfect for an animal that hunts in shallow water by looking up toward the surface. Vision is not the anaconda's primary sense, however. The forked tongue, constantly flickering, delivers airborne and waterborne chemical particles to the Jacobson's organ in the roof of the mouth, a specialized chemosensory structure that interprets these signals as detailed information about what is nearby, what direction it moved in, how recently it passed. The labial pit organs, heat-sensitive depressions along the lips, provide the anaconda with a thermal image of its environment, allowing it to detect warm-blooded prey even in complete darkness at distances of several meters. Lateral line sensitivity, the ability to detect pressure waves and vibrations in the water through sensory cells distributed across the body surface, adds another dimension of environmental awareness. An anaconda in murky water, blind to visual targets, can still detect the specific pressure signature of a swimming bird, a wading mammal, or a large fish through the hydraulic information flowing across its skin. This convergence of sensory systems makes the anaconda extraordinarily difficult to approach without detection, and extraordinarily effective at detecting prey without itself being seen. Part 5. Ecosystem Role. The green anaconda is an apex predator in a very specific and localized sense. In the aquatic and semi-aquatic ecosystems of South American floodplains, there are few animals capable of threatening a large adult anaconda. Jaguars will occasionally kill anacondas on land. Documented encounters suggest that the outcome of such confrontations is genuinely unpredictable, depending heavily on the sizes of the individuals involved. Large caimans are capable of killing juvenile and small adult anacondas. Humans, of course, kill them in large numbers. But otherwise, a fully grown female anaconda exists near the top of the local food web, constrained primarily by prey availability rather than predation risk. And the prey list is impressive in its breadth. Green anacondas take fish, particularly large species like peacock bays and armoured catfish. They take caimans, not the larger spectacled caimans, but individuals up to 2 meters in length are documented prey items. They take large rodents, capybaras, the world's largest rodent, and itself a sizable animal reaching 50 kilograms, are taken with some frequency by large females. They take deer, peccaries, tapirs, large turtles and birds. The range of prey size available to an adult anaconda essentially spans the entire medium to large vertebrate fauna of the floodplain. This dietary range has significant ecological consequences. By taking prey from multiple trophic levels and multiple taxonomic groups, the anaconda functions as a generalist apex predator that helps regulate populations across a broad swath of the ecosystem. Remove the anaconda, and you might expect increases in caiman populations, capybara populations, large fish populations, cascading effects that ripple through the entire food web. Conversely, the anaconda is also a prey item, though primarily in its juvenile and subadult stages. Large herons take newborns. Tega lizards raid suspected birth sites. Large caimans take juveniles. The anaconda sits at the center of a web of interactions, simultaneously predator and prey, depending on its size and life stage. There's also the matter of nutrient cycling. An anaconda that takes a large capybara on the floodplain and digests it over the course of a week is effectively transferring nutrients from the terrestrial system into the aquatic one, its excretions enriching the shallow water where it spends most of its time. At population levels, this kind of cross-ecosystem nutrient transport can be ecologically significant, though it has been little studied in anacondas specifically. The anaconda's role as an ambush predator also shapes the behavior of prey animals in ways that extend well beyond any individual interaction. Capybaras modify their movement patterns, their grazing times, their selection of water entry points in environments with high anaconda density. Caimans that have experienced constriction attempts from anacondas become more vigilant at the water's edge. These behavioral effects, what ecologists sometimes call the landscape of fear, alter the distribution and activity patterns of entire communities, with cascading consequences for vegetation structure, nutrient flow, and ultimately the physical shape of the floodplain itself. Part 6. Human Connection and Conservation. The green anaconda and the human imagination have a long, complicated and frequently dishonest relationship. The indigenous peoples of Amazonia and the Orinoco Basin have coexisted with anacondas for thousands of years. In many of these cultures, the anaconda is not a monster, but a cosmological figure, a creator, a deity, a river spirit. For the Tisana people of the Colombian Amazon, the anaconda is associated with the origin of humanity, a primordial being whose body is the world. For numerous groups across the region, the rainbow boa and the anaconda appear in creation myths as world shapers, their bodies forming the first rivers, their breath the first rains. These traditions encode a relationship of respect, even reverence, that stands in striking contrast to the fear and hostility that European colonialism imported along with its own mythology. European encounter with the green anaconda produced stories of staggering exaggeration. Early explorers and naturalists wrote of anacondas measuring 15, 20, even 40 feet in length, figures that, when traced back to their sources, invariably dissolve into second-hand accounts, rumour, and the motivated distortions of men who wanted to make their travels sound more dramatic. The legacy of this exaggeration persists. Hollywood has produced multiple major films built around anacondas as monsters, their sizes inflated to absurdity, their behaviour pure invention. In reality, the documented maximum length for a green anaconda, achieved through actual measurement rather than estimate, is around 8.8 meters, achieved by a female captured in Colombia. That is extraordinary enough. It requires no embellishment. The damage done by this cultural mythology, however, is real. Anacondas in many parts of their range are killed on sight by farmers who fear for their livestock, by fishermen who believe them threats to their catch, by rural communities for whom the snake is simply a large and frightening thing that deserves to die. This persecution is not offset by any targeted conservation effort. There is no dedicated international protection for the green anaconda. It is not listed on CITES Appendix 1. It falls into the broad category of least concern on the IUCN Red List, which reflects not its abundance but the imprecision of our data. We do not, in truth, have reliable population estimates for green anacondas across their range. Large constrictors are extraordinarily difficult to census. They are cryptic, solitary, and distributed across vast and largely inaccessible habitats. What we do know is that the threats are real and increasing. Habitat loss and the conversion of Amazonian and Llanos floodplains to agriculture, the damming of rivers, the drainage of seasonal wetlands, eliminates the slow water habitats the anaconda depends on. Climate change is altering the timing and intensity of wet seasons in the Amazon basin in ways that disrupt the flooding cycles that organize the anaconda's entire life history. The skin trade, which at its peak in the mid-20th century exported millions of snake skins from South America annually, has been curtailed by legislation in some countries but continues informally in others. There is also the emerging threat of road mortality. As road networks expand through previously remote areas of the Amazon and the Pantanal, anacondas crossing roads during their seasonal movements are killed in numbers that may be locally significant. A species that reproduces slowly, matures late, and has low intrinsic rates of population increase is poorly equipped to absorb sustained adult mortality from road strikes. Research efforts are improving our understanding. Long-term studies in Venezuela's Llanos, particularly at the Hato El Frio Wildlife Reserve, have produced some of the most detailed data available on anaconda population biology, tracking individuals over years, documenting seasonal movements, estimating population densities, and establishing basic demographic parameters. These studies have been invaluable. They have also revealed how much we still do not know. There is a growing movement among herpetologists and conservation biologists to establish more formal protections for the world's giant constrictors, to acknowledge that these animals, which occupy apex positions in their ecosystems, deserve the same level of systematic conservation attention that we give to large terrestrial predators like tigers and jaguars. Whether that movement will translate into policy changes before populations are significantly reduced is, at this point, an open question. What is not an open question is the ecological importance of these animals. Where anacondas are present in healthy numbers, the ecosystems they inhabit tend to be structurally complex. Prey populations tend to be more balanced, and the overall biodiversity metrics tend to be higher. They are, in the technical language of conservation biology, a species whose presence indicates a functional, intact ecosystem. Their absence would not go unnoticed. It would be felt across the entire food web in ways that might take decades to fully manifest. Part 7. Final Thoughts. We began this story in a flooded backwater with a female anaconda in the act of giving birth. Depleted, motionless, her work done, and her young already dispersing into the murk around her. It seemed, at first glance, like an ending. a mother's story concluding at the moment her offspring's stories begin. But now, having followed the anaconda's life across its full arc, we understand that those two stories are not separate. They are the same story, told in different registers. The newborn's first frantic weeks in the shallows echo the experiences of its mother at the same age. Its first prey, its first shed, its first close escape from a heron's bill. These are the same passages, run again. The breeding ball, the long gestation, the birth. These too will come if it survives long enough. The cycle is not metaphorical, it is literal. It is the mechanism by which continuity is achieved, generation by generation, across millennia. What we've seen in the green anaconda is an animal shaped by time in ways that confound our usual categories. It is ancient in its origins, a representative of a lineage that was old when the Andes were young. It is extreme in its dimensions, the heaviest snake alive, an animal whose body mass places it in a category occupied by very few other reptiles in Earth's history. It is metabolically inventive, capable of fasting for months, restructuring its own organ systems around the demands of digestion or reproduction, shrinking and expanding its metabolic rate in response to circumstances in ways that still surprise physiologists. And it is, in the most fundamental sense, patient. The anaconda's success is not built on speed or venom or agility. It is built on the capacity to wait, to remain still when everything around it is moving, to persist through dry season and flood, through lean months and rich ones, through the long stretches between meals when the water is low and the prey is scattered and the sun is unrelenting. This patience is not passive. It is a form of power, accumulated over evolutionary time, expressed in every coil, every strike, every slow revolution of the metabolic wheel. The newborns we watched enter the water at the start of this episode are by now long gone into the vegetation. Most of them will not survive the year. The ones that do will grow, slowly, into animals of increasing consequence, progressively larger, progressively more capable, progressively more central to the world they inhabit. In 20 years, if everything goes right, one of those tiny hatchlings might be a 5-meter female lying in a shallow backwater in the Venezuelan llano, surrounded by the flickering of her own young entering the water, and the cycle will have turned again. What this episode set out to understand was the shape of a life, how a creature begins with nothing but instinct and scale, and becomes something that can hold a caiman still. The answer, it turns out, is not dramatic. It is not filled with sudden transformations or explosive revelations. It is a story of incremental accumulation, of meals, of sheds, of seasons, of years, of a body growing slowly larger against a backdrop of flood and drought and predation and competition, until it has grown large enough to no longer fear most of what once threatened it. In the end, the insane life cycle of the green anaconda is not insane at all. It is precise. It is refined. It is the product of millions of years of trial and error, of death and survival, of the relentless pressure of a living world on a lineage that refused generation after generation to stop. And somewhere in a South American river right now, a shape is drifting in the current, perfectly still, perfectly patient, waiting. If you enjoyed this episode of Animal Uncovered, following the podcast is the best way to support the show. And if there's an animal you want us to uncover next, leave a review or comment and let us know. Until next time.